So welcome to our seminar on technologies and measurements for beyond 5G, also looking at the topic of 6G. As an introduction, we know that 3GPP has started work on 5G Advanced from release 18, and now of course industry and academia is evaluating technologies for 6G. Anritsu is participating in multiple projects and consortiums to help define and shape these future telecoms technologies and the related measurement requirements, which is something we'll be looking at in today's seminar. There are a number of key technologies such as sub-THz frequency devices, full duplex transmission, AI ML in the air interface, disaggregated virtualized networks, all photonic networks, and energy efficiency. And these are all central themes for networks beyond 5G. And we'll be looking at a few of these topics also during the course of this seminar. So let's look at the research topics overall, and we have a graphic here to try and represent the different areas in the telecom network which are being looked at and researched in the industry. So we start at the baseband, distributed and compute processing, so spreading the processor load across the different compute elements is one research topic. And this is closely linked to the all-photonic network and defining new protocols and architectures for a network architecture. And we'll look at this a little later in the presentation. Also then are new coding schemes for the baseband transmission. And then over on the device side, we're also looking at research into adaptive and software-defined radios. So although software-defined radio has been around for many years, this has not really been used heavily within the cellular industry. And now for 6G, there may be opportunities to use software-defined radio in the mobile device. Also, as the processing and data rates increase, we may also see the use of onboard optics, so optical interconnect and optical computing, even within the device side of the system. As we look to the radio TXRX, so the transceiver functionality, we can see both on the network side and the device side, development for native AI ML. So we'll talk later on this, but really to design in from the start, artificial intelligence and machine learning into the radio functions. We see also on both sides the research into terahertz band device technology, and we'll look a little more detail on this, but the typical frequencies at around 300 gigahertz are being intensively researched at the moment. Then also for the network side, the use of full duplex transmission, which can offer up to doubling of the capacity of the network, and is a topic that was first introduced in 5G but not implemented in the 5G standards, and now being reviewed again for 6G. On the antenna side, we also see the use of artificial intelligence machine learning, particularly for assisting MIMO channel modeling and for the MIMO propagation algorithms, that we can improve the MIMO data rate performance by using AI/ML. Also then we can see that intelligent arrays may be introduced, so the antenna could have more intelligence in terms of its beam forming and beam pointing capabilities. As we look at the propagation channel itself, there is a lot of research now on the terahertz band channel modeling and characterization to see if it's going to be suitable for cellular communications and what kind of performance and use cases we can expect. Also then, reconfigurable intelligent surfaces, RIS, are a new research topic. And we'll look at one slide later on this topic and understand a bit more of what's happening. But important to note that RIS is not specifically terahertz band, and is in fact much more to do with the lower frequency bands used in the network today. Finally then, energy efficiency and the green network requirements. So of course this has become a very important topic for the whole industry to reduce carbon footprint and improve energy efficiency of the network. So this has got a lot of attention and a lot of research activity for beyond 5G. Now let's look at the timeline, the frequencies, and the possible spectrum utilization for beyond 5G. So we can see that currently 5G is in its full launch phase. So here we are just entering 2022 with many 5G networks launched or in their deployment phase at the moment. And from 3GPP, we've just started now to work on release 18, which is the 5G advanced. So 5G from a standards point of view is now moving to 5G advanced and adding new features and capabilities on top of the base 5G network capability. And then we would expect to see from mid 2020s, so 25, 26, that the beyond 5G and 6G network launches could be starting. And this is aligned to the 3GPP releases, maybe release 20, release 21, not certain yet. And as far as the frequency bands are concerned, we can expect to see the ITU's World Radio Communications Conference, WRC. So WRC 2023 is expected to be identifying some spectrum suitable for 6G, for example, terahertz bands. And then by WRC 2027, we might start to see some allocation of spectrum. So looking at the standards, looking at the spectrum, we could start to think that 6G networks could be deployed 2027, 2028, that type of time frame. Today, of course, we have the industry 6G technology research, which is our topic for discussion today. And then in 1 or 2 years' time, around 2024, we could start to see the pre-6G prototypes and industrial solutions, and also start to see the 3GPP study phase starting from maybe release 19 onwards, with the 3GPP specifications expected again around mid 2020-26 period. So there's been a lot of discussion on terahertz technologies and bands. This is because there's, of course, massive amounts of new bandwidth available in terahertz bands. So tens of gigahertz of spectrum could be available to operators, allowing for massive data rates and many new types of use case. However, at these frequencies, there are fundamental limitations due to the propagation of signal at this frequency. There is a massive loss due to absorption of signals and very different behavior in terms of scattering and diffraction of signals. So there's a strong push from the research community to investigate and develop techniques that can overcome these fundamental limitations at terahertz band. Let's not forget then the lower frequencies, so the existing FR1, FR2 bands, which are used in 5G today. And there's of course got a lot of focus on improving the efficiency of this spectrum, as we envisage that this existing spectrum will also evolve towards a 6G type of technology. So as we looked on the last slide, a lot of interest in using AI ML to improve the efficiency, particularly then dynamic spectrum sharing, real-time sharing of spectrum, and instantaneous use of the spectrum. Also then AI ML can allow for an intelligent radio that can adapt itself according to local conditions. And when we start to combine intelligent radio with intelligent coverage from spectrum sharing, we can really have a highly optimized spectrum utilization in the future network. And then we have topics such as full duplex for a base station, which gives us simultaneous transmit and receive, and could allow some new access schemes to be used to optimize this type of technology. So looking then at these terahertz, and particularly in what we might call sub-terahertz band around 300 gigahertz, what are the test and measurement challenges that we can see in this area? Well, traditional RF measurement equipment uses a harmonic mixer for up and down converters, as shown on the right-hand side here, where a signal generator, AWG, is up converted to an antenna to transmit a signal, and then down converted to a digitizer to analyze. The problem we have is that these up-down converters have known issues due to image response and harmonic spurious response. So this creates many unwanted responses and unwanted signals, both in the transmit chain and the receive chain that we try to analyze. Also, these harmonic mixers are very sensitive to local oscillator noise, and so it has very high demands on the local oscillator and ends up with normally quite a high noise system. Also then, these types of architectures have got relatively poor phase and amplitude stability over wide band. And here we're talking about 10 gigahertz of bandwidth. So maintaining high phase stability over 10 gigahertz of bandwidth becomes very, very demanding. So what we need to do is we need to say, well, how can we ensure good image suppression, good out-of-band measurement and good OTA measurements where there would be other signals present in the band? Because to measure a transmitter OTA or with its outer band, we need to have a very pure and clean signal interspectrum analyzer. So this is where a preselector is used for suppressing any image frequencies from the mixer. And this becomes then a really important part for a sub-terahertz spectrum analyzer, is to have the preselector filter technology. Also then, to look at the phase stability issue, phase stability is needed to do wideband calibration of a transmitter. For example, for beam steering, you need to accurately calibrate the phase response of each antenna feed. And so to do this, we need a phase stable sampling system in the test equipment, because of course the test equipment has to have much better phase stability than the signal we're trying to measure. And so we need to develop a highly phase stable sampling system to ensure that we can make an accurate phase compensation of a sub-terahertz transmitter. So in Anritsu, we've been looking at these terahertz technology topics and have several research activities underway. The first is looking at the 300 gigahertz spectrum analyzer. And as we said, the pre-selector filter becomes a very, very important topic here, required if we're going to use up and down converters. And so Anritsu has developed a proof of concept of a spectrum analyzer that operates at 300 gigahertz, so actually operating 255 to 315 gigahertz. And is able to do swept spectrum analyzer measurements across the whole band here. And this is done using the pre-selector filter. So we have reduced and actually fully suppressed the image responses and the spurious responses of the harmonic down converter. So this means we can do accurate and useful OTA measurements of sub-terahertz transmitter devices. For the phase compensation scheme, so shown on the right hand side here is a diagram of a system that we have developed, which is actually using electro-optic sampling methods. So driven by a pulse laser, we can electro-optically sample the transmitter waveform and make very highly stable, phase stable measurements on the output, and use those phase stable measurements to compensate the transmitter nonlinearities into a receiver processing. And so this has been demonstrated and shown very important and very good improvements in the, for example, the EVM of a received signal, where we've been able to improve it from around 19% EVM before the compensation scheme to around 6% EVM after compensation. And this is all due to having a very highly phase stable electro-optic sampling system in the test architecture. Finally then, when we're looking at semiconductor devices in these sub-terahertz frequency bands, we need to do actual circuit simulation to model and to design these circuits. And the circuit simulation is based on device models which are generated through a vector network analyzer. And so in Anritsu, we have our ME7838G and G4 broadband systems. And these are able to sweep from 70 kilohertz to 220 gigahertz in a single sweep. And this allows us to do really the world's best characterization of devices and wafers at these frequency bands, and enables developers to have the most accurate device models and most accurate device performance modeling within this sub-terahertz band region. So beyond those testing challenges, some of the other radio technologies that we need to look at. First of those is the full duplex transmission that we mentioned earlier. So Current wireless communication systems separate the transmit and the receive signals, either separating time with a TDD system or separating frequency with an FDD system. And this is to prevent the transmitter and receiver interfering with each other. And transmitter to receiver interference can be either self-interference or cross-link interference. And these two are shown in the diagram below. On the left-hand side, we have self-interference from the base station, the BTS, where its own downlink signal to one UE is actually interfering with the uplink from another UE because it's transmitting at the same frequency at the same time. And it's self-interference from the base station transmitter to base station receiver. On the right-hand side, we see cross-link interference. And here, for example, there are two base station antennas, and one is transmitting and the other is receiving at the same frequency at the same time. And they're interfering across to each other. So not from their own device, but across to another device. And the same is shown on the bottom here for the user equipment, the UEs, where we have cross-link interference between one UE and an adjacent UE because they're both trying to use the same frequency at the same time. One is uplink, one is downlink, and this is causing interference to the UE in the middle. So we need to find ways to overcome this self-interference or cross-link interference to use full duplex transmission. So when we can overcome this restriction, we can increase capacity 2 times because we can use all of the frequency all of the time for both TX and RX. And this is a huge step forward for telecom systems. So looking on the bottom left here, we see that in 2G, 3G, 4G, we always had a fixed duplex. So it was either a TDD or an FDD system. Already in 5G, we have what we might call a flexible duplex, where the FDD bandwidth can be changed in the system. The TDD time slot pattern can be changed in the system. So 5G can be flexible in its duplex, but it still needs to have some duplex between the transmit and receive side. And in release 18, we have a new study item looking at some new duplex arrangements which could be more flexible and more adaptive to network conditions. However, this is still not reaching our full free duplex that we would like to achieve. So the 6G research is looking at how can we achieve the diagram shown above, which is where we have a base station which is really free to transmit and receive on all time slots in all frequencies without any self-interference. And so this is the big challenge at the moment, is to move from the flexible duplex that we have today to the full duplex. On the bottom right-hand side, we're showing a reference from the Samsung 6G white paper, where we're considering here that we could have some sub-band full duplex. So there may be some part of the band suitable for full duplex. And so we can be adaptive in the network. In some parts of the bandwidth are used in flexible duplex, but other parts could be used in full duplex if conditions are allowed correctly. So this is the expected direction we would go into, is a sub-band full duplex to start with. Another important technology topic which has a lot of attention at the moment is the Reconfigurable Intelligent Services, RIS. So we can show the diagram on the top left here. And the theory is that I have an array of M passive elements here which are able to reflect a signal. So the signal H coming from the source is reflected and becomes signal G heading towards the destination. And rather than being reflecting like a mirror where H and G are operating at the same angle and is a reflection, by adjusting the phase response of each element, the direction of G can be adjusted. So that the reflection is not symmetrical, but is directional, and we can direct the reflection towards a specific destination. And if we take that one step forward, we can add a RIS controller into the base station. And this is able then to coordinate with the base station the direction of certain reflections which are needed towards certain user devices. So shown now is we have a signal H coming from the base station, but there are 3 different reflections, G1, G2, and G3. And these are all aiming reflection onto specific user devices 1, 2, and 3. So now we can actually ensure that this RIS surface can overcome blockage of signal and can allow me good coverage and good signal to each of the user devices, where they can be actually moving or in different locations, and the reflective property of the RIS is specific to each user device. So this technology, both in terms of the reflector technology itself, but also the RIS control and how it interfaces the base station, and the channel sounding that we need to determine the path for each of the user devices. This is the big research area that we have at the moment. And shown on the bottom here is one of the typical measurement examples. So normally we use a vector network analyzer, VNA, to measure the reflection of the signal off the RIS surface. And normally we'd use a full 2-port VNA, so we can see all the reflection terms, both the S11 self-reflection, the S21, which is the required reflection towards the device, and also looking in the opposite direction, so from the user device to the base station, the S12 and the S22 parameters. And so Anritsu has the very recently introduced ME7868A, which is a distributed VNA, so we can do these full 2-port measurements, but able to separate the two antennas by hundreds of meters. So we can move out of a very small lab benchtop and actually go out in the field and allow some measurements of a real RIS antenna performance out in the field. So another topic we want to cover briefly, which has a lot of attention across the whole of engineering, I would say, not only in telecom, is artificial intelligence and machine learning, which is being applied to many situations in the world today, of course. So on the first side, we want to talk about AI. So AI, artificial intelligence, and in the context of telecom, is closely linked to distributed computing. So we see on the diagram here our distributed computing concept, where we have a core cloud, core network, edge cloud, and then the small cell. And we know that if we put all of the computing into the core cloud in a centralized location, although we have all the data together, there's a data bottleneck, because all the data needs to be transferred across from the end user to the core cloud. So high amounts of data flowing through all of the network. And this has a related cost in terms of running the network with so much data. If we move the AI towards the edge, we will have more cost effective, because the data doesn't need to go all the way through the core network. And also it helps us with latency, because the distance that the data travels from the end user to the AI processing is a much shorter distance. So it helps us with latency and it helps us with a cost-effective scaling. But the third step is to do local AI, so the end user device itself, the sensors in the device can actually do AI on the original raw data before it's transmitted over a telecom network. And this will further minimize the data that needs to flow through the network. However, when we look at AI, the algorithms today are very compute intensive. They take a lot of time and use a lot of power. And often for some of the physical layer procedures in the network, they actually take more time and more CPU power than a dedicated physical layer processor. So the architecture we have today, before AI ML, is maybe more power efficient and more time efficient. So AI needs to improve to be implemented into the RAN so that it can become time efficient and power efficient versus today's dedicated algorithms and today's dedicated accelerator hardware boards, which are giving our best performance in the market currently. But we expect that the algorithms for AI will improve and will be able to surpass the dedicated algorithms and the dedicated accelerator boards in the future. So some specific areas of AI and ML which are of high interest. We said earlier, one is the massive MIMO beamforming and the scheduling. And here then, for example, the CSIRS, so the channel sound indicator reference signal, is being able to read the CSIRS and optimize it for the best channel performance. Also then for millimeter wave beamforming, we have a beam training. So based on the channel characteristics, could we learn how to do the beamforming in the best possible way and not use fixed algorithms that we have today for beamforming. So these two examples are two where we will try to first apply this on 5G, which will give us some incremental improvement in terms of the CSIRS or the beamforming in 5G. And then once we've made an incremental improvement on 5G, we can actually apply it onto 6G to get an optimized solution in an all new 6G type of configuration. So besides the AI then, we've got the machine learning, ML, and the other interesting topic we have for 6G is the ML-enabled air interface. So we want the air interface between the network and the UE to become dynamic and able to configure itself based on machine learning algorithms. So the two elements, the transmitter and the receiver, can collaborate with each other and have some kind of neural network approach to deciding on the waveform, the coding, and the access scheme. This, of course, requires some joint training, some joint model sharing, and distributed learning. So both the device side and the network side need to be training together, sharing the model, and learning together on the channel. But if we can do this, then we can start to improve many areas, shown here like the MIMO scheduler, the interference coordination, coordinated multi-point transmission scheduling. And on the device side, the beam management evaluation, the CSI evaluation, and use machine learning also for positioning and sensing capabilities. So 5G services use a function-based interface where the AI is applied externally. So 5G, each function has a static function, and then externally AI can draw data from the function, process the data of the function, and return a decision to the function. So here the AI is actually sat outside of the 5G service function itself. For 6G, we want to bring the AI inside of the function, so embedded into the architecture of the 6G network, and the AI and ML flowing across the different functions and interfaces. And this could give us a lot of benefit in handovers, which is some end-to-end consideration of a network, coverage optimization, very importantly then the energy consumption and energy optimization end-to-end across the network, and self-healing, so the network has some problem or some fault that it can learn how to fix or work around problems. So these are all the examples of a native AI ML embedded into the architecture of 6G. And we have three different tiers at which this AI ML would be working. So there's local AI in each element, so the UE, the RAN network, the core network, and the application elements, each doing their own local AI ML to optimize the local decisions. But at the same time, we need to have joint AI between different elements to allow some interactive and predictive decision making. An example we showed at the top here of having the radio interface where the base station and the UE are sharing a channel model and then are sharing information on interference coordination or for CSI information. This is a joint AI between two elements. Then the third area is the end-to-end AI. So this can be used to predict or to identify problems and to propose a corrective action in the network. This is using, of course, now all of the network resources available. So we go back to our left-hand chart and our end-to-end diagram, going from end user through the 5G network, the network edge cloud, the core network, and the core cloud. If we have end-to-end AI across here, we can then start to do things like the self-healing and the end-to-end optimization of the power consumption by using this end-to-end AI. All of this then requires standardized and open interfaces so that the KPIs between the different elements and the analytics data between the elements can flow very easily across the whole network. So, final technical area we'd like to look at is the ION, the Innovative Optical Wireless Network. And this is a activity coming from the ION Global Forum, looking at the core network and the transport network evolution for the future. There are three main topics within the IOWN study area. The first is full stack communication. So using what's shown on the diagram here as the cognitive foundation. So this is a new higher layer stack, protocol stack, to replace the TCP/IP. So the TCP/IP stack has been used in the telecoms industry for many years and has been efficient in transporting data across networks, but it is no longer efficient enough when we have many different types of use cases and requirements. So looking at using this cognitive foundation to provide a new protocol stack and an adaptive protocol stack for managing the higher layer configuration for an end-to-end communication. Also then looking at using the all-photonics network plus wireless network, and shown in the diagram here is the onboard optics approach to this. So on the left-hand side at the bottom, we have the traditional server architecture where we have physical servers connected, and shown here in the red is the route going from one disk through to one AI execution. And we can see that it travels through the green, which is electrical circuits, and then the yellow, which is the optical connections. So the signal has to transfer between many different protocols. So it goes from a disk to a PCI interface to a CPU to a PCI interface to a NIC interface to an optical network interface. Many interfaces becomes complex and actually has bottlenecks. On the right-hand side, we see now the onboard optics all-photonic network implementation. And here there is a very simple route going from the disk to the local memory, and it flows all the way through a single photonic network without the need for multiple transitions, without the need for multiple converters from optical to electrical and reverse. So this end-to-end all-photonic network offers a much more data efficient and much more high capacity route for all the processing within the AI ML environments. Finally then, in line with the first part in terms of the full stack communication, is to move the whole centricity or the whole concept of the data communication. On the bottom left-hand side in red, we have a traditional network, which is IP-based network, where all the data from each sensor and all the data for each processing element is converted into TCP/IP traffic, and all TCP/IP traffic flows across the IP network. On the blue chart then, we see the cognitive foundation data hub concept. And in here, each of the sensors, so from the vehicle or from the camera or from the person, actually has its own functional dedicated protocol. So depending on the type of data, the capacity, the latency requirements, the protocol stack can be adaptive towards the function that's required. Then equally on top of this blue chart, where we have the different compute databases, functional compute, photonic database compute, all of these can be configured with specific protocols that allow a much more efficient use and transport of the data. Of course, this architecture still needs to be compatible with TCP/IP and the legacy network. So we would see it as an extension to the existing TCP/IP network, but opening up many more opportunities for transport of large amounts of data, high capacity and low latency across worldwide networks. So to summarize what we've been talking about today, so beyond 5G and 6G, the use cases are not clear yet. The industry is just starting to define the use cases. The target is to bring new capabilities in 6G, things that are not possible in existing 5G-based wireless communication. So it's not an incremental step up from on 5G, but it's all new capabilities of 6G. And also we see that there's a transformation from a business value to a societal value. So for 6G, we may have a wider scope than the 5G use cases, looking at many issues such as the environmental issue on the green network and the energy efficiency, looking at issues like the digital divide and empowerment of communities and ensuring all communities have got good and efficient access to this technology, that it's scalable, that it's affordable for all of our communities to use this technology. And as said, the environmental impact becomes a very important priority for future telecom networks. And some example here from the NGMN white paper on future network, highlighting these areas of societal benefits, of differentiated services, novel from what we can do from 5G, and the necessity to create and deliver enhanced value so that it becomes open for everybody in our communities to use this technology. The central themes that we have within the use cases are still starting to coalesce together. One central theme is a digital twin, so where the physical, the digital, biological worlds converge, often called cyber-physical convergence, where we can live in a cyber world, live in a physical world, and bring those two together and interact between cyber and physical worlds. The other central use case is for a real-time immersive experience, so full holographic images, so that when you look at an image, when you hear some music, where you see a video, you can become fully immersed three-dimensionally in the environment and have holographic images to show you the environment that you're in. So we've looked at some of the fundamental technologies which are underpinning this vision for beyond 5G. We've talked about the terahertz and sub-terahertz frequency bands, which would have new modulation coding schemes for the wide bandwidth, new channel modeling requirements, and an evolution of MIMO for us. We also consider the spectrum efficiency, including spectrum efficiency at the existing FR1, FR2 bands, with things like virtual MIMO, the full duplex, the advanced spectrum sharing, and the RIS, Reconfigurable Intelligent Surfaces. And we discussed about having AI and ML designed native into the air interface and native into the cellular architecture, and embedded native into the operations and maintenance and the orchestration of the network. So all the functions of the network have the AI ML embedded inside of them. We've also talked about disaggregated network and distributed computing, and how distributed computing works very closely with AI ML to allow us to dynamically share across the UE, the RAN and the core network, to share the computing and the processing load that's associated with the AI ML concepts. And finally, then we looked at some of the future optical network technologies that should enhance the network efficiency, the network data rates, and the latency. And looking at the ION project, we could see all photonic networks, onboard optics, and silicon photonics being important fundamental technologies for the future. So finally, then, we had a little look at some of the test and measurement technology for the spectrum analyzer at 300 gigahertz with a novel pre-selector filter, looking at the wideband calibration techniques, looking at the measurement requirements both for terahertz band device technology and also the measurement requirements for the RIS testing and evaluation. And the test and measurement technology will continue to advance in line with these fundamental technology evolutions that we show above, to ensure that we can bring the right test solutions and the correct test technology to the market on time. So that concludes our look at beyond 5G and 6G technologies. Thank you very much for your time.